Did you ever imagine how liquid mixtures are separated into its pure components like water and oil?
Or a homogeneous mixture of ethanol and water?
Or a solution containing water and acetone?
Acetone? I just used it yesterday to remove my nail polish. Look, my nail is already clean.
Ooh.
So how do we separate them? I think distillation is the process we're looking for. Say we have a binary mixture, the yellow smileys represent the less volatile component, and upon application of heat, obviously, the temperature will also increase. Hence, the kinetic energy of the molecules also increase, such that the more volatile component wanted to escape. However, some of them stays. Then, through condensation, they can go back to their liquid form. This distillation in a laboratory scale. As chemical engineers, we would like to produce that in a larger scale. We use a process called scaling up. And instead of a flask, we operate in a distillation column.
Now let's talk about distillation columns. Basically, there are two types of distillation columns, the packed column and the plate column. As the liquid mixture enters the column and heat is supplied through the boiler, the more volatile component goes up while the less volatile component goes down. Now let's take a closer look.
This is what happens. The plate can be bubble cup or perforated plate. Let's consider the simpler one, the perforated plate. The gas passes through the holes or perforations, making it distributed. As it comes into contact with liquid, simultaneous heat transfer and mass transfer takes place. Mass is transferred simultaneously from liquid by vaporization. And from the vapor by condensation. Now, let's take a look on the stepwise design tray procedure. Step 1. Determine the number of theoretical plates as well as the vapor and liquid flow rates separately both in top and bottom section. Then we will go to step number 2 where we will obtain the physical properties of the system, which includes density, viscosity, as well as the surface tension. Step number 3. Select a trial plate spacing. Then we will go to step number 4 where we will estimate the column diameter based on flooding considerations. Step number 5. Decide the liquid flow arrangement. Step number 6. Make a provisional tray layout including downcomer area and active area. Step number 7. Check the whipping rate. If not satisfactory, then we will go back to step number 6 and reselect tray layout. If satisfactory, then we will go to step number 8, where we will check the plate pressure drop. If it's too high, then return to step number 6. If satisfactory, then we will go now to step number 9. By checking the Downcomer top up. If it's too high, then go back again to step number 6 or number 3. Step number 10, we will decide the plate layout, and if it's unsatisfactory, then return to step number 6. Step number 11, we will recalculate the percentage of flooding based upon selected tower diameter. Then, step number 12, we will check for the entrainment. If it's too high, then return to step number 4. Step 13 is optimizing the design. We will repeat the steps number 3 to number 9 to find the smallest diameter. Step number 14, finalizing the design. Draw up the plate specification and sketch the layout.
Our task is to design a continuous distillation column to recover acetone from 50% mole acetone and 50% water mixture, available at 30 degrees Celsius. The feed rate is equivalent to 25,000 kilograms per hour. The top product should contain at least 95% mole acetone, while the bottom product should contain less than 1% acetone by mole. We will consider the reboiler as equivalent to 1 stage. This is operated at 1.25 kilopascal per tray. 60% efficiency will be assumed. Step 1, we determine the theoretical stages. Using the McCabe and Thiele method, we obtain the number of trays where we get 6 above and 3 below, which is a total of 9. But for the real number of stages, we subtract 1, which is equivalent to the partial reboiler, and divide it by the column efficiency. Then we get 14 as the number of stages. Also, using this method, we shall also determine the liquid and vapor flow rates both for the top section and the bottom section. We use L for liquid and V for vapor. These are the values you obtain. Step 2, we estimate the properties of the physical system. First, we are given that the column tray operates at the atmospheric pressure equivalent to 101.325 Pascal. Then we assume that there is 1.25 kilopascal per tray. Multiplying it by 14, we get the column pressure drop. For the top section, the following values can be obtained by considering that this section operates at the dew point of acetone and at atmospheric pressure. The density, molecular weight, and surface tension were obtained. For the bottom, properties were obtained using the column pressure drop plus the atmospheric pressure, which is 118,125 Pascal. Using steam table, density for saturated liquid and saturated vapor were obtained. Molar masses and surface tension for vapor and liquid were obtained using component mass balance. Step 3, we select the trial spacing. For this step, we use this table. Initially, we assume that the tower diameter is greater than 1 meter. Thus, we get tray spacing equal to 600 millimeters.
Step 4, determining the column diameter. Column diameter is associated with area, and area is associated with volumetric flow rate and velocity. To obtain the maximum flooding velocity, we use this formula. From this formula, we need CSV. and this can be determined by using this graph. On the x-axis of this graph is the flow parameter, which can be solved directly. Assumed earlier that the tray spacing is 600 mm, CSP is equal to 0.12. Substituting it to the formula, we get that the maximum flooding velocity is 2.26 meters per second. To get the actual vapor velocity, we multiply it by 0.8 as percent flooding. Now, let's compute for Qmax and is given by this formula. Direct substitution, we obtain 6.98 cubic meter per second for the Qmax. Dividing it by the actual vapor velocity, we have the net area. Usually, net area occupies 90% of the cross-sectional area of the tower. So, dividing it by 0.9 gives us the tower area and the tower diameter, which is 2.38 meters. This diameter is taken considering the flow rates at the top section. Doing the same method for the bottom section by considering the flow rates at the bottom, the tower diameter that will be obtained is equal to 2.36 meters. The nearest recommended shell has a nominal diameter of 2.4 meters. So for the next calculations, we will use this nominal diameter.
Step number 5. The selection of liquid flow arrangement. This graph is going to be used. On the x-axis, we need the column diameter, while on the y-axis is the liquid flow rate. From step number 4, we calculated that the column diameter is equal to 2.4 meters. The liquid flow rate on top is equal to 0.012 cubic meter per second, while the liquid flow rate on the bottom is equal to 0.007 cubic meter per second. And projecting it on the y-axis, we select the single pass cross flow. So, among this liquid flow arrangement, the single pass cross flow sieve plate is chosen for this service.
Step 6. Provisional plate design. This includes dimensions necessary to construct plate, wear, and downcomer. For the column diameter that we obtained before, we have 2.4 meters. From this, we can obtain the column cross-sectional area, and that is 4.52 square meters. For the downcomer area, it is the area where liquid flows from top to bottom. So, this time we choose that it is 10% of the column cross-sectional area. For the net area, we calculated it before, and that is 0.9 of the tower cross-sectional area. Now we have 4.068 square meters for the net area. For the wear length, 60 to 80% of tower diameter is normally used. Here we use 0.73 of the tower diameter, and that is, we have 1.752 meters for the wear length. Active area represents the area available for vapor just above the tray floor. It is just tower cross-section area minus twice the downcomer area. So we have 3.616 square meters. So let's take a look on plate side view. For the first trial, we consider that the plate thickness is equal to hole diameter, and that is 12 millimeters. Step 7. Checking for whippage. So, what is whippage? Whippage happens when at low vapor flow rates, liquids start to leak or rain through perforation. This happens when the actual vapor velocity is less than the whip point velocity, and we do not want this. So now, let's compute the whip point velocity using this formula. This formula, we need K2, and we get K2 from this graph. On the x-axis, we need the maximum wear crest, and this can be computed using this formula. Substituting the value of LWC as the maximum liquid flow rate, LW as the wear length, and ρL as liquid density, the resulting liquid height is 27.2 millimeters. HOW is the minimum wear crest, and this can be computed by multiplying the maximum liquid flow rate by 0.7. Substituting the values for LWC, LW, and ρL, we obtain the value of 21.5 millimeters liquid height for the minimum wear crest. Adding the two and plotting it on the graph, we have 30.3 as K2. Substituting the value of K2 as 30.3 and DH and ρV, we obtain the whip point velocity as 12.6 meters per second. The actual vapor velocity should be greater than this. So to compute for the actual vapor velocity, we divide the actual vapor flow rate by the whole area, and we have 10 meters per second for the actual vapor velocity. Doing the same for bottom section, finding the minimum vapor velocity and the actual vapor velocity, we obtain that the actual vapor velocity is greater than the whip point velocity. And that is what we want. However, going back to top section, the minimum whip point velocity is greater than the actual vapor velocity. This actual vapor velocity can be manipulated when some of the holes are closed to an extent that the actual vapor velocity is greater than the whip point velocity.
Step number 8, checking for the plate pressure drop. At the start, we assume the plate pressure drop is 1.25 kPa per day. So, in this step, we will determine whether the actual pressure drop is too high. The total pressure drop is represented by this equation. HD, or the maximum dry pressure drop, can be determined using this equation. C0, or the orifice coefficient, is interpolated using this graph. But first, we will be needing the percent perforated area. This value can be taken from this graph. Assuming that LP over TH is equal to 2.5, we can get AH over AP. Then, we must multiply it to 100 and interpolate it to the graph, and we can get C0 equal to 0.88. Substituting this value to HD formula, then we can get 37.5 millimeters liquid. We have already determined this value earlier. So now we will go to HR, or the residual height. This value can be determined using this equation. Substituting the density, we can get 16.8 millimeters liquid. We have this, and this, and this. Now, we can add them all to get the total pressure drop, which is 122 millimeters liquid for the top section. Doing the same for the bottom section, we can get the total pressure drop equal to 122 millimeter liquid. Therefore, the estimated value in the first trial is acceptable.
Now we proceed to step 9, where we determine the Downcomer backup liquid and residence time to avoid flooding in the column. The Downcomer backup is given by the following equation in terms of the clear liquid, where HD is the head loss into the Downcomer and HB is the Downcomer backup. The head loss can be obtained by the equation, but first we determine the clearance area under the Downcomer AP given by. Then we get the height of the bottom edge of the apron of the plate HAP, which is 5 to 10 millimeters below the outlet wear height. AAP is smaller than AD, thus we use AAP. Now we substitute the obtained values to get HDC, which is equal to 8.8. Substituting, the resulting Downcomer backup is equal to 198 millimeters. Half the plate spacing plus wear height is greater than the HD, thus the design is satisfactory. This ensures that flooding does not happen.
Step 10. Plate layout. This includes setting calming zones, determining number of holes, and the hole pitch. So why are calming zones important? Inlet calming zone helps in reducing excessive whipping in this area because of high vertical velocity of the entering liquid in the downward direction. While the outlet calming zone allows disengagement of vapor before the liquid enters the downcomer area. Now we determine the number of holes. This can be done by using the equation and choosing that the area of holes is 15% of active area. We should have 4,326 holes in each plate needed to be punched. So how these thousands of holes be equally spaced apart to each other? By means of hole pitch. Hole pitch is the distance between the center of two holes. So to determine the distance between them, we use this equation in which we already know the hole area and the hole diameter. What we don't know yet is the perforated area. So how to determine the perforated area? Using this figure in which shows the cross-section of the plate, the perforated area is enclosed by red curve in the figure. To determine this, it is the active area minus the area of the calming zone minus the area of the edge strip. The edge strip is the gray area while the two vertical strips are the calming zone. Usually, the length of the calming zone is 50 to 100 millimeters. The alpha here is the supplementary angle of the angle subtended by the wear length, and upon substitution, 3.49 meters is the length of the edge strip. The area of edge strip is the calming zone times the edge strip, and again upon substitution, 0.175 square meter is the area. We should determine first the length of the calming zone by adding wear length plus the length of the unperforated edge strip. Thus, the length of the calming zone is 1.802 meters. The area of calming zone is only twice the area of the vertical strip. The area of calming zone is 0.18 square meter. Now we have the active area, the area of calming zone, and the area of the edge strip. The perforated area is 3.26 square meter. Substituting it to the formula, the hole pitch is 29.5 millimeters. This is closer to the one we assumed before, in which the hole pitch is 30 millimeters.
Steps 11 and 12. Determining the percent flooding and the entrainment checking. Entrainment is the phenomenon in which liquid droplets are carried by vapor to the tray above. The less volatile liquid component from bottom tray are mixed with liquid, having more volatile materials on the overhead tray. Increasing air velocity will increase entrainment. To get fractional entrainment, we use this graph. But first, we will get the L over G times rho G, rho L raised to 0.5, and the percent of flood. Percent flooding can be determined using this formula. It is the ratio of actual vapor velocity and the maximum flooding velocity taken from step 4. The actual vapor velocity is calculated using this formula, Qmax over AN. Substituting the value, we can get 1.7 meters per second. Substitution of the actual vapor velocity to the percent flooding, we can get this value. Using FLG equal to 0.033 at 76% flooding, then the fractional entrainment is equal to 0.09, which is the fractional entrainment for the top section. For the bottom section, same procedure will be used for determining the percent or the fractional entrainment. Usually, fractional entrainment less than 0.1 is desirable. And since our actual flooding is below the design flooding value of 80%, then our assumptions is valid. However, the optimum design value may be above this.
Step 13. Design Optimization. For us to optimize our design, we would have to go back and repeat a few steps. These are steps number 3 and number 9. Our goal now is to determine the smallest diameter of the tower and also to agree on an acceptable plate spacing. With an optimized design, the cost will be reduced. Step 14. Design finalization. Finally, we would have to whip up the following things: the plate and tower specifications and the sketch of our column layout. Once we are finished with both, we can now rest in peace. The design will be subjected to further reviews and calculation rechecking if the design is to be fabricated. This is to ensure less errors and failure upon operation.